In our last video, we looked at how we could use logarithms to solve an exponential equation. In this video, we're going to do the reverse and see how we can use exponents to solve a logarithmic equation. Before we get to that though, like in our last video, we had a very easy example to start with. In our first example, what people notice right away is both sides of your equation have log base 5. So if you notice that both sides have the same exact logarithm, then just cancel that out. All we have to worry about is getting the number or the pieces inside the parentheses equal to each other. So we don't need to do anything special for these ones, nothing advanced. Just put your two parenthesis parts equal to each other. So I'm going to subtract x from both sides. I would get 3x on this side. Adding 7 to the other side gets me 12. And then dividing by 3 gets me x equal to 4. Now with these problems, you'll see this note at the bottom of the screen. We have to make sure that we check our answers. If you recall, we had said previously that the domain of a logarithmic equation was x had to be greater than 0. You couldn't do the logarithm of anything negative or 0. So what you need to do is take your answers, plug them back in, and make sure that what you're doing the logarithm of, so not necessarily x itself, but what you're doing the logarithm of, is not going to come up 0 or negative. In this case, we're fine. 4 plus 5 is 9. 4 times 4 minus 7 is not negative. So 4 is okay. But we do have to make sure we check these logarithmic ones. Okay, anyway, on to the real problems, the ones where I don't have the same log on both sides. There's two ways you can approach these problems. I'm going to show you both methods. The first is called exponentiation, which is this word up here. And what that means is we're going to use a base to get rid of a logarithm. In this case, it's log base 7 that I want to get rid of. And so what I'm going to do is I'm going to exponentiate both sides by 7, meaning I'm going to make 7 the base on either side. I'm not raising both sides to the 7th power. That's an important thing to note. I'm making 7 the base. 7 raised to the log base 7 are considered inverse operations. Again, you may want to go back and watch a previous video about inverse operations to see how that worked. So they will cancel each other out, leaving behind just x. On the other side, then I have 7 now raised to the 3rd power. 7 to the 3rd power is 343. So that's how exponentiation works. Let me show you how to do the same problem with a different method if you don't like to exponentiate. And I actually like this other method a little bit better. With this method, all I'm going to do is rearrange the logarithms like we first learned how to do when we first learned logarithms. So I want to rearrange this into exponential form. 7 is my base. I want to raise that to the 3rd power. Remember, we said the answer was an exponent, and then that should be equal to x. So simply rearranging like we're used to doing is another way to solve logarithmic equations. X equals 7 to the 3rd is the same thing we got last time, which is 343. So let's take a look at a couple more complicated examples. I'm going to show one of these with exponentiation, the other one with simply rearranging the problem. So in this first one, I think I'm going to do my rearranging trick. So in this case, 4 is my base. I want to raise that to the 3rd power, and I'm going to put it equal to what's inside of parentheses. So equals 5x minus 1. Just rearranging it gets me something without the logarithm, and that's what I want to solve. 4 to the 3rd power is 64. Is equal to 5x minus 1. I'll add 1 to both sides, so 65 is equal to 5x, and then divide both sides by 5 and come up with an answer of 13. Now remember, I do need to check these before I just move on. In this case, what I'm doing the logarithm of cannot be negative or 0. 5 times 13 minus 1 is definitely not going to be negative. I know I said I was only going to do it one way, but I changed my mind. Let me show you how this same problem would work using exponentiation. So I want to get rid of a log base 4 in this case. So what I'll do is make 4 the base on either side of this equation. Not raise both sides to the 4th power, but make 4 the base. Doing 4 raised to the log base 4 cancels that out. I'm going to kind of do my work in orange over here, leaving behind just 5x minus 1. On the other side of the equation, I have 4 raised to the 3rd power. We'll take a look. That's the exact same thing I ended up with when I just rearranged it. So from there, it will work out the same. So I don't care how you do these, whether you like to exponentiate like I did in orange, or whether you like to just rearrange like in green. Either way is a great method for solving a logarithmic equation. All right, let's try one more. So in this case, it's a natural log I want to get rid of. So if you're thinking this is going to involve an e at some point, you're absolutely right. Take care of any of this other stuff first, though. The getting rid of the logarithm will be the last thing that we do. So in this case, I have a plus 2 I want to get rid of, so I'll subtract 2 from both sides. So 10 is equal to 5 times the natural log of x. I've got to get that 5 out of there before I can start working on the natural log. Since it's 5 times natural log, I'll divide both sides by 5. And then end up with 2 is equal to the natural log of x. At this point, maybe you want to rewrite the problem. Remember, natural log is the same thing as log base e, so I can rewrite the same exact problem as log base e of x. That may help you see what to do for this final step a little bit clearer. So once again, you're able to either exponentiate or simply rearrange. If I exponentiate this time, since my base is e, I'm going to make e the base of either side of this equation. So I will have e to the second power is equal to, well, doing e raised to the log base e will cancel out, leave behind just an x. And remember, e is just a number, so using my calculator, I can type in e and square it. And that's how I come up with my final answer of about 7.39.